Okay, can you guys hear me okay out there? Yes, I do have a lower body. I'm not just like Max Headroom, if you get that reference from the 1980s, just a talking head. Although I was strapped to my chair for 2 hours this morning creating this chat session, so I hope it's enjoyable for you all. So we'll get started in about 2 minutes at 11. Okay, so I think we can go ahead and get started. Hopefully you can all see the screen here with the agenda slide. I thought what I would do first is just take you through a tour of Canvas, Module 3 tour. So just show you again the layout with the synopsis, required readings, and chapter learning outcomes. I'll show you the Wiley assessments. So we're doing 3 chapters for this module, 3, 4, and 5. So I've sort of lumped these together and I call them physical organic chemistry, and I'll explain what that means. Your exam 3, which is the same format as the prior exams, will be on Friday, October 16th. And then there's a professional development activity in which you'll create a LinkedIn account. Then we'll look at Allegra, which is an antihistamine in relation to the Chapter 3 material on acidity. And if there's time, we'll do some the workbook pages from the first semester second language book. So let me just show you briefly in Canvas. So presumably you clicked on this link here to get into today's chat. There are 2 PDFs that if you could go ahead and download that we'll be using in today's chat. The first one is the structure of Allegra, where we're basically identifying the functional groups present. The second one is a pKa table, that basically associates a functional group with a pKa number, and that's the number that we're going to use for acidity. So those two pages will be useful for you today in the chat. So again, this is the module page. So modules, and we scroll down. Now we're on module 3, which I'm calling Physical Organic Chemistry, Acidity, Reaction Mechanisms, Conformational Analysis, and Stereochemistry. So if you click in the synopsis, this tells you what the big picture of these 3 chapters are. Your required readings are chapters 3, 4, and 5. So we're going to look at acids and bases, and then we're going to start our foray into our first functional group, alkanes and cycloalkanes. Really, that's more, not so much about reactions of those, but learning about specific properties in, then we'll transition into stereoisomerism. So when we've talked about wedges and dashes for bonds, we'll really get into why we use that convention. Again, your chapter learning outcomes, these are the things that you need to be able to do to demonstrate proficiency in the material. So they have these active verbs here: summarize, recognize, explain, classify. So if I were writing you an exam, I would look at these chapter learning outcomes and I would say, okay, there's probably about 25 of them. I would try to write one question per each of these that you could answer that would demonstrate proficiency. So your module assessments, as we said, there's 3 homework sets, 3, 4, and 5. 3 Orion sets, 3, 4, and 5. Engagement activities, so the LinkedIn account is one of them, your exam 3. And then the total module points are about 172, or about 1/5 of your grade. So here's the schedule that we're going to go through for assigning basically parts of those chapters for each day. So let me go back to module 3. So the lecture screencasts are here. The team chat recordings will be posted here. This is the link to the chapter reading, and then this is the link to the homework and link to Orion, so you can see that they all sort of follow that format. Again, please link through Canvas into Wiley Plus so that your grades transfer over properly. Any questions on that in the chat? The professional development activity, so there's directions here. So I try to include stuff like this that is more forward thinking in terms of your future career. You can never start too early for this. LinkedIn is basically a website where you can create a resume. You can click this link to see what mine looks like. But you need to do all these different things to earn your points. And then once you create your account, you'll submit the web link to me, and I'll use the speed grader and assign points. So I don't see any questions, so we'll go ahead and get started. So our molecule of the lecture is Allegra. So this is sort of what your standard pill box looks like. The one below it, it's called fexofenadine hydrochloride. And basically this is, Sanofi Adventis sells this, and then the generic, which is the same thing, but it's called fexofenadine. I think Top Care is maybe Walmart or something. So this brand is the generic brand of this drug. So presumably Allegra was a prescription drug at one point, and then it went off patent and other companies make it, and so that's called a generic. So here's the structure that we're going to look at quite a bit today. And so what this molecule is, it's an antihistamine, as you see in the slide here. And so it's anti is against. What is histamine? This molecule here, this small molecule, is called histamine. And so what happens when, like, spring and sort of in this fall, there's like really high pollen count. That can be like an irritant. And so your immune response is to release histamines to sort of attack that foreign body. And so an antihistamine basically is seeking to quench how much of this histamine is present. So if you've ever had an allergic reaction to something and you get like crazy swelling, swelling is good to some extent, but if it's too much, it's bad. So an antihistamine will, like, in this case, prevent like the runny nose, the eye watering, and that stuff. So I'm going to ask you over the next series of slides, some basic questions about fexofenadine or Allegra that relate to acidity and basicity. So there's a little movie. You can see this sort of looks like a spaceship out of like Halo or something. You can see how, these two aromatic rings, they're sort of in this portion of the molecule, like this shape they give to the molecule. Then you have these sp3 hybridized carbons. You have the nitrogen in this chain that sort of elongates it until you get to the other ring. And then you have these methyl groups and then the carboxylic acid. So biologically speaking, the shape of the molecule is interacting with basically an enzyme that prevents the histamine from either being made or shuttled somewhere. So the shape matters, and the shape comes from the functional groups. So let's get to it. How many degrees of unsaturation are there in Allegra? So this is sort of a visual inspection. So again, I really want you to start connecting these topics rather than thinking of it as just like a straightforward question. The correct answer is A, it's 13. Or no, sorry, it is not. It is not A. I got caught up in the chat peer pressure. As we see it, it is B. I think it's 14. So we have 4, 8, 12, and then this is 13. And then, yeah, here's number 14 buried in the acid. So the way that the acid is communicated to you, you don't necessarily see the carbonyl, but it's there, and it's 1 degree of unsaturation. So what do I want you guys to think about? Not just visually counting that stuff, but when you look at the molecule, the unsaturation should, in your mind, you should start thinking about, how does the proton NMR look? How does the carbon NMR look? And how do those signals resolve one another? So that's sort of how you can thread these things together. So you have 4, 8, 12, 13, and then the acid is 14. So I hope you see through the progression of this chat session how all the topics from week 1 until now are threaded together. So how many unique carbons are there in Allegra? So unique number of carbons. Again, there is a couple elements of symmetry to the molecule. So what I mean by saying that, if I asked you to determine the molecular formula, you'd come up with a certain number of carbon atoms. this question is asking you, of those carbon atoms, how many are unique? And if there's symmetry, that reduces the total number. So I'm seeing some answers of D as in dog. So 19, let's go through and count them. So there's 1, 2, these are the same, that's 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19. So this ring and this ring are the same. So these are the same. These two and these two, that's all one set. Then these two, that's one set, and these two, that's another set. So the answer should be 19. So now I'm gonna probe a little bit deeper. And again, these are just basic questions probing what you already know, but we're going to connect it to acidity and basicity. So how many total of each type of carbon hybridization are present in Allegra? So notice it says total now. So you're counting all of the carbons, and then you're putting them in these different hybridization bins. So how many total sp3? How many total sp2? How many total sp? So we're looking at total. We're not reducing that number by symmetry at all. So just using some logic, when on a visual inspection, you can eliminate A. There's no alkyne in the molecule. There's no nitrile. There's no other sp hybridized carbon functional group. So we can eliminate A because that's 1. It looks like from the chat, most people are picking C, which is the correct answer. So let's go ahead and count those. Start with the sp3 hybridized carbons. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. So that's 13 sp2s. There's 6, 12, 18, and then 19. And then we said there was no sp, so we've accounted for all the different hybridization types. So the next question, of the 13 sp3 hybridized carbons, which of the following correctly categorizes each present in Allegra? So now you're only considering the sp3 hybridized ones. How many are methyl? How many are methylene? How many are methine? Or how many are quaternary? Again, quaternary means there's no hydrogens bonded to that sp3 hybridized carbon. So I'm seeing the majority of responses is A. So let's go ahead and count those. So methyl. So again, a lot of organic chemistry is like things are, there's, if you've ever like listened to Richard Feynman, who won a Nobel Prize in physics, he talks about like describing things, the difference between describing something and knowing something. So methyl, so we say methyl, we can abbreviate it capital M small e or CH3. So if we look here, that's another sort of abbreviation of methyl, even though it's not written CH3, we sort of at this point know it's methyl. So there's 1, 2, then all of the rest of the sp3 hybridized carbons, there are no more. So there's 2. Methylene is CH2. So we have 1, 2, 3, 4, 5, 6, 7. Methine is CH. That's this 1, 2. Quaternary, there's 1, 2. So we've so far in this semester, we've learned what methyl, methylene, methine, and quaternary mean. Now we can apply it to this sort of problem. And again, it's important for us to know how we're communicating these things, because as you'll see, as this builds up, it's going to be important. So of the 19 sp2 hybridized carbons present in Allegra, how many of them have hydrogen atoms? So yeah, Taka said some of them don't sum to 13. So yeah, those would be the ones that you could eliminate as the distractor answers. So in this one, there's 19 sp2 hybridized carbon atoms. How many of those have hydrogen atoms? So how many total? Looks like we have sort of a debate. We have a Trump-Biden debate, C versus D. Who's going to win? Who has the better answer? C versus D. So I'm curious why some people pick what they did. So the power of persuasion is at work here in the chat. I like it. So we have some thought processes evaluating back and forth. The correct answer is C, it's 14. So you have 5 here. So 5, 10, 11, 12, 13, 14. This hydrogen, as Ian points out, is bonded to the oxygen. It's not bonded to that sp2 hybridized carbon. So that's why C is the correct choice and not D. So again, it's important to realize what is being communicated by this condensed formula that represents the carboxylic acid functional group. You know what I mean, the connectivity of those elements present. So let's look at another one. And so this is going to be our transition into elevating what you know how to do to the next thing that's appropriate for chapter 3. So how many unique sets of hydrogens are present in Allegra? So again, this is sort of the classic hydrogen NMR type question. So there's a couple responses of C in the chat. Let's go ahead and count that. We have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, knowing that this ring and this ring are the same. So Aiden points out something to do with chirality. I sort of laugh in the sense that I know your book presents that, but that's a layer of complexity that I don't particularly teach to sophomores because in relation to NMR, I mean, we're going to get into stereochemistry and chirality. This carbon right here is a stereocenter, and we will talk about that. But what we're not going to talk about that is how that's going to like increase or make other hydrogens different. So your book, as you may have read, uses like enantiotopic or diastereotopic. I don't particularly teach that to sophomores because the fundamentals are what matters here. So so we're just going to focus on this number here, 16, which we just counted. Now what I want to do in terms of acidity, and this is the slide. I'll switch over to the doc cam as well. So this is in the module link on how you got to this Teams meeting today. So here is Allegra in the center. So there are 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16 boxes. So each box corresponds to the unique type of hydrogen atoms that you just identified. Now what we are going to do is we just did a visual inspection. Now I want to make an association of what functional group that type of hydrogen belongs to. So for example, see where my mouse is? And I'll write it on the sheet that's projecting on the document camera as well. So where my mouse is, and you can in the chat box as we go through this, what type of functional group is this pointing to? Carboxylic acid. I see many uses of the caret. I believe that's called the caret character. Could be wrong. So let's go up to this one now. So I'm on the screen, I'm in the box above it. What functional group is this now? So these two. So they're methyl groups. That is correct. But what's a more general name for that functional group? Like the broadest name you can think of. So alkane. So yeah, it's an sp3. sp3 hybridized carbon H. So down here, that was the acid OH. So what about here? What functional group is this? Can't tell if there's been a response or not. So yeah, this is an alkane as well. So again, it's sp3 hybridized. It's methylene. So we're just really, the questions we just did before, we're just sticking them directly on this structure now. So if you look along this manifold here, same thing, alkane, alkane, they're all methylenes, right? See sp3, H-type bonds. They're all methylene, CH2, CH2, CH2. Now what about this hydrogen here? How would you, what functional group would you call that? So Taka says alkene, Aiden says aromatic phenyl. So aromatic is probably the better functional group descriptor. Aromatic phenyl or benzene. So this is CsP2H. The reason we don't want to say alkene is because when you see this carbon-carbon double bond next to one in a six-membered ring, it's and let me just say this. The alkene double bond is not the same as a benzene double bond. So the benzene takes priority, and that's how we're gonna classify it. So these next two are the same sort of functional group, aromatic, CsP2H. Then what about this one? What functional group is that? So that's a tertiary alcohol. Then what about this one? So I'll move my mouse. We're over to here right now. So yeah, we're back to alkane. This is CsP3H, and then this is a methine. So sort of this and this are the same. We've sort of seen those already. Alkane, alkane, CSP3H. And those are both methylene. So what about this one now? So yeah, that's a secondary alcohol. So where do we get this secondary from? So look at the carbon bearing the OH group. It has 1, 2 carbon groups. So 1, 2, that means it's secondary. Over here, we said this one was tertiary. It has 1, 2, 3 carbon groups. So that's tertiary alcohol. And now this box here, it's pointing to this carbon that I just highlighted. So what sort of functional group is that? So alkane, sp3 hybridized carbon H, methine. Then these last two, we've sort of seen aromatic. CSP2H, aromatic, CSP2H. So hopefully you can all see this sheet that we just wrote on. Looking at this sheet, we said there were 16 unique types of hydrogens. We assigned functional groups to each. How many functional groups did we just assign? How many different functional groups? So maybe I'll take the purple pen now. So I see alkane. Everywhere I see alkane, I'm just going to underline. Alkane, 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 alkane. So let me write that here. So with purple, we underlined all the alkanes. In red, maybe I'll do the aromatics. So green, I'm going to do alcohols. We have 1, 2. Then maybe in this sort of pink, purplish, the only thing left is acid, carboxylic acid. So there were some responses in the chat about 7, which I can understand. But really the best answer is 4. So again, you know how to look and visually inspect for uniqueness. We just assigned functional groups to each of those. And then lumping all the different functional groups together, we came up with alkane, aromatic, alcohols, carboxylic acids. So these are the different types of hydrogens that are present in this molecule. And sort of what I mean, we can sort of break this down. See here, alkane, aromatic, those are CH, right? Regardless of the hybridization, it's still CH. And then alcohols, carboxylic acids, those are OH, right? So we sort of have two main classes amongst these four functional groups, right? And so on our next slide, as you see, we've put in those responses, what we did on the sheet here. So you can see those are now filled in. So as we see on the bottom, it says, we therefore have two main types, CH versus OH, based on four different functional groups: alkanes, aromatic, alcohol, carboxylic acids. At this point, we don't really need to go into the granularity of like primary versus secondary versus tertiary. That's probably where you got 7 from. Let's just focus on the main functional group names. So just to recap here, we came up with CH versus OH spread among 4 different functional groups: alkanes, aromatic, alcohol, carboxylic acids. The next slide states our goal for chapter 3. Our goal is to understand the reactivity, or more specifically, the acidity of these different types of hydrogen. So now we're going to use the tabular data, again, that's the other PDF, to associate the functional groups we just identified to a number that is called pKa, and then rank those functional groups from most acidic to least acidic. So here is that table. So we're going from, we're taking those 4 functional groups. We want to look on this table, and this is a table that it's from the prior book that organic chemistry was using. Your book has a table like this, but it's not as detailed. But again, you have access to this PDF. Let me switch it over to the .chem as well. Again, this is posted in Canvas. This table here, we're starting very broad on the practical skill of what you need to do, and then we're going to go in sort of the theory of acid bases. So look on this column here, where it says acid. These are the different functional groups, sort of what we already determined. So we want to look for alkane, benzene type, alcohol type, and carboxylic acid type. So see where it says acid in this column? Then there's this number here, and then it says conjugate base. So if you look at this species here, where it says strongest acid, it gives you this number. It says -12. So we'll go through what that means, what the scale is. Then it says conjugate base. Notice this is neutral. The conjugate base has a negative charge. And so what happened? You lost this hydrogen. So the reactivity of a CH, OH, or NH bond that reactivity is called acidity. So if something acts as an acid, the proton is donated. So it loses the proton. If it starts neutral, it ends up with a negative charge. So these are the different functional groups, and the burden on you as the student is to look at this column, and they're not giving you, like, see this methyl group? They're not giving you a specific methyl group associated with Allegra. So you have to go on this column and see, okay, which one of these best matches a methyl group? And so it's down here. You have sp3 hybridized carbon, you have a CH3 group. So ethane only has one unique type of hydrogen, CH3. So it's sp3 hybridized. So this methyl group is best associated with this functional group on this table. So those type of CH have this pKa value. See the center here, it says approximate pKa. That number is 50. You can see the prompt here, it says weakest acid. So these are really weak. They have a very high pKa number 50. So the pKa scale is typically as I wrote in the chat, that's sort of the scale we're working on. Sort of 50 up to -10. The farther, again, you can sort of think of this as NMR. You know, in proton NMR, you had methyl groups that occurred between like 0 and 1. And the more sort of substitutions you do on the carbon, the more you sort of change the acidity. So the weakest acids have pKa's about 50. And so if you look at the difference between the acid here and the conjugate base, you're removing one of these hydrogens. So the neutral species becomes negative. So let me maybe I'll just do it on this sort of handout in the appropriate color. So we said the alkanes were about 50. Now the aromatics, if you look on here, there's not really a benzene ring anywhere. So we really have to just say, okay, this sp2 hybridized carbon H, that best mimics an aromatic CH. So we can say its pKa is 44. And really, I'm going to explain how you get these numbers, but now it's just about interpreting the table. Can you find the functional group and find the pKa? So looking at the screen, now look at the screen. Can you find where alcohols lie? What number should I write next to alcohols here? So in the chat, write what pKa is associated with an alcohol. Morgan, that's a smidge too high. This is, if you look, this is an alkyne. These are the sp hybridized carbons of alkyne. So this is acetylene. Taka, that's a bit too low. Katie and Annabelle are sort of right on in the mark here, 16 to 18. So see the OH here, OH, then water is 15.7. So we're gonna write, I'm just gonna say 16. Now what about carboxylic acid? Where do you see that on the table? So 4.75, there you see it. You have ethanoic acid. There's your acid functional group right there, 4.75. So what did we just do? We determined the total unique type of carbon, or excuse me, hydrogen. We associated the functional group. We then looked on that table, found the pKa values, and I've written them here in the sense that this is the most acidic. And this is the least acidic. Taka asks, what's that 4.21? That's another carboxylic acid. But notice the group bonded to it is a benzene ring. So I'm not particularly picky about these things. Again, you're not taking exams that I'm writing. So what is my best advice? So rather than trying to memorize, like say a carboxylic acid is 4.75, just call it 5. By reducing the number of digits 4.75 to 5, acid is 5. Alcohol is 15. So 0, 5, 10, 15, 20, 25, 30, 35. Associate it sort of like that rather than like specific numbers like 10.2 or 19. Just round it to the nearest sort of unit of 5 to relieve the mental burden. So I would say 5, 15, 45, 50. So this is what we just did. We used this table to quantitate the acidity of these functional groups. And why is this important? Because we want to understand the reactivity of each type of hydrogen. And you can sort of see the line already, right? We said these were CH, these were OH. Look at this huge difference that occurs. So on this side, the most acidics are OH. The least acidics are CH, right? Can you, in the chat, think of a reason why why hydrogens bonded to a heteroatom are more acidic than those bonded to carbon? If you've done some of the reading, this might be pretty straightforward, but even if you haven't, why would you think this is the case? So Tenley and James are quick to answer that and say electronegativity. And that's really, I think, the best answer that I would give is that, remember, we're dealing with polarization of that bond. So if oxygen's more electronegative than hydrogen, the bond is already polarized towards oxygen, which means this is a weaker bond, which means if this is an acid, it's more readily donated. We don't really have that polar separation in a CH bond, remember? We don't really say these are polar bonds. So they're less acidic. And so if we go through that same slide as you see on the slide deck now, what I've basically put into each of these boxes is the pKa associated with each of those functional groups. And why is this important? So the acidity order is acid is greater than alcohol, greater than aromatic / benzene, greater than alkane. Say you are, look at our molecule here, Allegra. If you treat this molecule with one equivalent of a base, the carboxylic acid is the first hydrogen that is abstracted because it is the most acidic. So why is that important? If you worked for Sanofi Aventis as a medicinal chemist and your boss came to you and said, look, the pollen's going to be really bad in the next couple years. We need a new derivative of Allegra that's more potent than Allegra. We need to reduce the milligram dosage that the patient takes. So what is a way to do that using organic chemistry? You do everything you just did, then you can say, okay, I'm going to go in the lab, treat this molecule with one equivalent of base. I know it's going to remove this hydrogen first. I can then transform this acid, say, into an ester. Then I can test these ester derivatives for their antihistamine ability. And so that's how you make derivatives of an active pharmaceutical ingredient, or API. So hydrogen reactivity, known as acidity, is important to us because that's how we make a lot of new bonds. So using that logic, you deprotonate this, you do a reaction with some carbon species, you make an ester. If you were to deprotonate this is the next acidic one, right? So a second equivalent of base would deprotonate one of these alcohols. And as we'll learn in Module 4, when we start talking about mechanisms and reactions, we can deprotonate here, then react with another species to transform the alcohol, which is polar, into an ether, which is less polar, right? So really what you should be doing now is making these associations of functional groups with pKa. This table is posted in Canvas, and we will go through how these numbers arise and why are other reasons they go from weak to strong. But now it's really a specific functional group in the condensed formula, and then moving over to see what the pKa value is and making those associations. Any questions on this before I have a few more questions I want to ask you guys before we transition and before the chat session ends. But any questions on sort of what we've done so far? So a couple more questions, some basic knowledge. Which of the following correctly characterizes the reactivity profile of an acid and a base? So yeah, an acid is a proton donor. A base is a proton acceptor. So acid donor, base acceptor. So another thing we're going to do in this chapter, in chapters 6 and 7 as well, is look at how a base actually drives the reaction. The analogy that I like to use is a quarterback throwing a football to a receiver. That is, according to the rules of American football, that is the vector of how things have to go. The quarterback has to throw the football to the receiver. The base has to abstract the hydrogen from the acid. And we're gonna show you the drawing convention of how the electrons move to accomplish that. So our next question, what is the name of the molecule or ion that forms when an acid loses its proton? So it's the conjugate base. So when you're given a reaction, an acid-base reaction, so there's two species on the reactant side and then two species on the product side. So you have acid-base, then you have conjugate base, conjugate acid. One of the learning outcomes is for you to identify those pairs and understand why they're associated with one another. So one last question. Which of the following is the conjugate base of sulfuric acid H2SO4? So H2SO4 is a diprotic acid. If it loses one hydrogen, what is the conjugate base? So B as in boy is the response that we're seeing. So yeah, that's correct. You're losing one of the H's bound to the oxygen. It therefore has a negative charge. So in this chapter, we're going to learn more about functional group acidity, how acid-base reactions happen, and we'll talk not only about hydrogen transfers between molecules, such as like with sulfuric acid, but we'll also talk about Lewis acid bases, which is the most general theory there is, because that focuses specifically not on the movement of hydrogen, but the movement of electrons. And that's important as we transition into the reaction mechanisms later on in Module 4. So we're about out of time. All the homeworks and all the Orions are now open to you, so I strongly encourage you, I'm begging you, please do 3 to 5 problems per day. Please do not wait until the night before the exam. That does you no good. If you have questions, shoot me an email. We can set up a 30-minute meeting. But other than that, I'm going to go ahead and sign off, and we'll see you Friday, okay? Take care.